All right. So when the black screen happens, that means my camera's getting ready, and when you start to see something again, that means we're recording. So we're going. We're going. Yeah. So exponential growth and decay functions is what we're looking at in 6.1 here. Oh, and just so you guys know, we will use those student journals quite a bit. From what I've heard, probably not as much as what Mrs. Court did with you guys. It was like a daily thing. I would say maybe like every other day or something like that. Maybe a couple times a week or whatever. So in that case, I can pause this, and then we can work on some stuff here and then come back to this and that sort of thing. So today we're not going to use the journals, but have them with you because we do use them frequently enough that it's worth dragging those along every day. So, all right. So an exponential growth and decay. So we need to start with what an exponential function actually is. Thank you. Hey, Trent, go ahead and have a seat wherever. I'll get you your stuff here in just a minute. But all right, so the equation of an exponential function always looks like this. A times b to the x. And the important thing to know here with this is that the a and the b are constants. Sorry, that's a little bit fuzzy. I got to get a new one of these cameras, I think. Anyway, it's different from some other functions that you've looked at because the a and the b are constants. They're just numbers. So a and b could be whatever. Maybe it's going to be y equals 2 times 3 to the x, or y equals 5 times 1/2 to the x, or whatever. But that x is always just x. That's going to be your variable, and the a and the b are always going to be some sort of constants. And depending on the value of the a and the b, the graphs of these things can look a little bit different. Okay? So we're going to start off with assuming that a is going to be some sort of a positive number. So if a is positive, we get two different things that might happen. Either it looks like this, or it looks like that. Now, which one of those two do you suppose is the growth, and which one of those two do you suppose is the decay? Yeah, the first one is the growth, second one is the decay. Okay, so it's getting larger as it goes. That's your growth. The other one is the decay. And so what determines whether it's a growth or a decay is the b. Okay, both of these, remember, is if a is a positive number. So depending on the value of b, we might have something that grows or something that decays. So if b is a number that is not a fraction, if it's bigger than 1, it's going to grow. So this is the case where b is greater than 1, and then the other one would be if b is less than 1. Or, I guess, technically, it can't be smaller than 0 either. So it would be just some kind of fraction that's caught between 0 and 1 would be the decay. All right, so that's pretty much what we're going to focus on is if I give you an equation of one of these things, can you tell me if it's a growth or a decay based on what you have for your b? Okay. And I guess one other important thing to mention about these while we got them here is this y-intercept where that comes through and crosses, that's always A. Okay, so whatever that first number is in the equation that you see, that should be the number where it crosses the y-axis, whether it's going to be a growth or going to be a decay. It's going to be right there. Now, if A happened to be something negative, I don't think any of the problems that you guys are going to deal with in here have any A's that are negative. Doesn't look like. No. Okay. A can be negative. What would happen to that would be, it was just these two graphs would be underneath the x-axis instead of above the x-axis like they both are. But that's not something apparently they're going to have you looking at in this section yet, so we don't need to worry about it. But just know for now that A is going to be something positive. So what I'm going to do is I'm going to give you guys a bunch of equations that are all exponential. I just want you to go through each one of them and just tell me, is it going to be a growth or a decay then? Okay? Based on the way it's put together. Oh, yeah, is that off the screen? There we go. All right. So for each one of those, see if you can figure out what's the A, what's the B, and then use that to determine, is it going to be a growth or a decay, if we were to graph it. Alright, and then I can, call on you guys randomly off of this on my computer. Let's see if I can do it. Yeah, alright. So, does anybody need more time, or are we good with those four? We're all good? Okay. So, first one, number one, let's have, oh, he's not here. Never mind. Madeline. If you want me to call you something different, just let me know. But oh, Hatfield. So is Madeline or Maddie or Maddie? Okay. All right, Maddie. So first one, what did you have? So growth or decay? Growth. Good. All right. Second one, Trent. What'd you have for that one? All right, we're doing this one or this one? I don't know. Second, this one here? Yeah. Okay. Even though it's got the 1/3 in front, that's the A, this is the B. So it's actually a growth. Right. So you're always looking at this number here to see if it's going to be a growth or decay. So that one's a growth. Number 3, let's see, Hannah Kelsey. Decay. Good. Yep. All right, and then number 4, Mr. Belka. Growth. To growth. Good. Okay, so just real quick, with each one of these, there's an A and a B. Okay. Now, the top two, it's a little easier to see what the A and the B are, and the bottom ones, maybe not so much. But A is 2, B is 5, A is 1/3, B is 2. What about number 3? What's the a? It's not 0. It's 1. Remember, we're multiplying, right? So anytime you're multiplying by something but you don't see it, it's technically a 1. So the a is 1, it's just not written there. You could put a 1 times 1/3 if you wanted. The b is 1/3. So again, the b determines if it's a growth or a decay. So this one's a decay. And then number 4, same thing. It's 1 times 4 to the x. The a is 1, the b is 4. So since the b is 4, that's a growth. Okay, so that's how you can identify those. Now you're going to also be asked these to graph what you have. Okay, so let's real quick run through that. So let's just graph, let's say 3 times 1/2 to the x. Okay, and anytime you're asked to graph something, it doesn't matter what kind of equation it is, you can always do the same thing. You just pick some values for x, plug them in, see what you get, plot the points out, connect the dots, you have a graph. Okay? So now there's usually some numbers for x that are easier to use than others. So what are some nice numbers you can use for x that tend to work out a little nice? Like 1, 0, maybe 2, -1, something like that. So what I usually do is I just stick with, and usually 5 points is good enough. Really you only need 3, but 5 is usually plenty. I'll just do -2 to 2. -2, -1, 0, 1, and 2. Just pick those 5, plug them in, and go. Okay? So we'll make our little chart here. Okay, and some of these we can do in our head. Some of them you might need to use your calculator, and that's fine. So let's see, if we do 3 times 1/2 to the -2. Okay, probably do that on your calculator. So here's how you can do that. So we're going to do 3 times 1/2, or just 0.5. And then if you want to do an exponent, because we want to take this to the -2 power, put the little caret in there, and then -2 in parentheses like that. You guys all done this before? Yeah. Okay. All right. So that's 12. Okay, so plugging in -2, we get 12. And the cool thing about, if you have one of these kind of calculators, if you go second and then hit enter, it'll put right in what you had before. So let's say I want to do -1 now. So I just go back and make that a 1 instead, and I don't have to keep typing out the whole thing. That's a 6. So again, second, enter. Now I want to make this a 0. I got to get rid of that negative though, so I'll delete that and then make that a 0. So that's 3. And then make it a 1. That's 1.5. And then a 2. That's 0.75. And now you get some ordered pairs that are ready to roll. So x, I want to make sure I'm between -2 and 2, and then y, I got to get all the way up to 12, and then go as low as 0.75. Okay. So give myself a little bit of space here with the x's. And then y, if I'm going to get up to 12, I was going to say go by 3s here probably, yeah, would be good. 3, 6, 9, 12. All right, so -2 got me 12, so that's going to put me there. -1 got me 6. 0 is 3. 1 is 1.5. That'd be about right there. And 2 is 0.75, so kind of there. All right, and then just connect those dots together. And graph looks something like that. So just by looking at the graph, do we have a growth or a decay here? Definitely a decay. And look at the equation we started with. That should make sense, right? What's the b in the original equation we started with? 1/2. That's a decay. Graph looks like a decay. Got it. Good. Okay. So like I said, though, when you want to graph one of these things, I would just go -2 to 2, plug them in, plot your points. Yeah?
Did you say we need to buy our own calculator?
If you don't have a graphing calculator of your own, I can loan you out one. You know what? At the end of class today, remind me. If there's anybody that's in that situation and needs one from me, we can take care of that today. That's fine. Okay, doing the graphing. What I have you doing is trying to figure out what the percent of growth is. It's kind of a different way that you can write an exponential function that's not just the a times the b raised to the x. So, but you can kind of convert back and forth between the two. So sometimes they look like this. Where it's 1 plus r to the x. Okay? And so that r represents the rate of growth as a percent. And so if you see an equation written in the other form, you can bring it to this if you want to figure out that as a percent. So that basically what that means is every time x goes up by 1, how much of a percent of the original are you getting as you go up? Okay? So, and some of these equations can be written kind of funky. So let's say we had something like f of x equals 2 times 4 to the x over 3, something like that. They even put like fractions up in the exponent. Well, there's some rules of exponents that you guys have learned before that we can use to help us get through this. So if you have x over 3 like that, really what that is saying, okay, we got 4 to the 1/3 power, and then that is to the x. Anybody remember what property that is? When you can take an exponent like that and kind of break it apart?
No.
Been too long? It's called a power of a power. If you raise something to one power and then raise that to another power, you can multiply those together, and then it's actually the same thing. So x over 3 is the same thing as doing 1/3 times x. So you can just take the 1/3 and bring it into the 4 first, and then raise that to the x. So if you use your calculator here, 4 to the 1/3 power, we can rewrite that as a decimal. Okay, so just like that, 4 to the 1/3. So we're going to figure out, basically we're trying to figure out what the b is right now by doing this. Okay, 4 to the 1/3, and that gets us 1.5874. Kind of round that off a little bit. So at this stage, then I can go 2, and then instead of this 4 to the 1/3, my calculator told me that was 1.5874 to the x. Okay, so now it's kind of looking a little bit more like what I've got up there, but that's 1 plus r. Okay, so if the base is 1 plus r, and I've got 1.5874, what's the r for this one? Yeah, if you just take the 1 off the number, right, that's the r. What's left over is the r. So in this case, my r is 0.5874. Okay, but what's 0.5874 as a percent? It's about 58%, or I guess closer to 59, right? About 58.74. So if someone asks you what's the percent of growth of this particular equation, it's about 58.74% then of growth. So you got a few problems in your assignment where you're going to have to switch some things around that way. Now this one has growth. Sometimes these things can be decays. So actually I'm going to go up here to the top again and show you. So if we have that instead of 1 plus r is 1 minus r to the x, then that's going to be a rate of decay, because you're losing that rate each time. You're not adding it on each time. So let me show you one of those real quick. So if we want to do a rate of decay one, so let's say I've got f of x equals 3 times 0.5 raised to the x over 2. So we can do kind of the same thing, okay? So this is then doing the 0.5 raised to the 1/2, but then that is to the x. And that's where you can use your calculator again to figure out, okay, what is that as a decimal? 0.5 to the 1/2. And I got 0.707. So let me take it out. So it's 0.7071. If we take it out 4 places again. So to figure out the rate of decay would be, okay, 1 minus whatever my rate of decay is needs to come out to 0.7071. So how much did I subtract from 1 to get 0.7071 is what you're really trying to figure out. It's going to be like 0.3 something or other, right? So if we do 1 minus 0.7071, yeah, I get 0.2929. So that's going to be about a 29% decay. So this one is a growth. This one is a decay. All right. So how can you tell, again, at the beginning of one of these, whether you're going to end up with a decay or growth?
B is greater than 1, it's growth.
Right. And you can tell that right from the beginning here. 4 is bigger than 1. It's got to be a growth. 0.5 is less than 1. It's got to be a decay. Or after you do the calculator step even too, right? 1.5874, that's bigger than 1, right? So there's a growth. This one over here, 0.7071, that's less than 1, right? So that's got to be a decay. So then you kind of know how you need to go from there then, okay? The growth ones are easy. You just take away the 1 and there's your answer. The decay ones are a little more difficult. You got to subtract from 1, but it's still, what do you need to subtract to get to that? So, yeah. So that's how you can figure out, even if they're written a little bit differently, whether you have a growth or a decay, and then even describe it a little bit further, how much as a percent of growth or percent of decay do you have going on. So we're going to do one quick story problem and then do a little finance stuff with some of these exponential equations, and then I think we're going to be good to go for today. And we're actually going to steal a question out of your textbook here. If you want to take a look, if you would, turn to page, well, it's right on page 300. We're going to do number 21. Because I don't want to have to write the whole problem out, so just turn to page 300. Yep. Oh, can you share with him real quick until I can get that for him? We'll do that at the end of class. All right. So number 21 in your textbook says, of a can be approximated by the model y equals 200 times 0.75, where t is the number of years since the bike was new. So first thing I'm going to do is I'm going to write down that equation they gave me, because that's important. All right. And so it's important to know what is y and what is t. So based on what I just read, what does y represent and what does t represent in that equation?
Y equals $1.
Okay. And what's t? Okay. And more specifically, bike, right, in dollars. And t is the years since the bike was new. So how old is the bike in years? A, tell whether the model represents exponential growth or exponential decay. Okay. So, what do we got going on here? Definitely a decay, right? If you take a look at the equation they gave you, A is 200 and B is 0.75, so that's a decay then. All right, part B. Identify annual percent increase or decrease in the value of the bike. Okay, so this is kind of like what we were doing before. We're focused on this right here. Now, it's a decay. So how did we do a decay to figure out the percent? You have to subtract from 1, this base. So what is the percent then? 25%, right? It's 0.75, but you got to figure out what do you subtract from 1 to get that? It's 0.25. So this would be a 25% decay. And then part C, estimate when the value of the bike will be 50. Okay, and here's where we're going to use our calculators to help us out. And this is where we need the whole graphing part of them. So that's why we need to have these guys going for everybody as soon as possible. Okay, so estimate when the value of the bike will be 50 bucks. Okay, so I'm plugging in 50 for what? Y or T? Y. Remember, Y is the value of the bike, right? So when the value of the bike is 50, how old is the bike? So we're trying to figure out T. Okay, always be careful about that. What are they giving me? What am I trying to find? They gave me a price, that's Y. I'm trying to find time, that's T. So I got to work this backwards and solve it. Now, one way you can solve it is using these things called logarithms that you haven't learned about yet, but you will later in this chapter. If you haven't learned about that yet, we can use a graph to do it instead. Okay, and here's how. If we take, first of all, go into y equals, clear out whatever is in there. So first of all, graph the original equation. So this is this 200 times 0.75 to the t. So we go 200 times 0.75. And you don't have t's, you have x's, but it's all good. Just caret x. Okay, so that's the original equation you started with. And then in the y2, you're going to type in what you want it to be equal to, 50. And what we're looking for is, where do these two things cross? Because you're going to have two graphs on here, right? One is the exponential curve, and the other one is 50. And we want to figure out where those two things intersect. All right. Now, we got to be able to see it, so we're going to have to make the window a little bit different here. Usually your window, oops, something changed on mine here. Usually your window is going to default to be in this. But make our y a little bit bigger because we need to go all the way up to 50. So I'm going to start my y at 0, my y min at 0, and the y max Maybe, let's say 100, just so 50 is right in the middle, so it's easy to see. Okay? And then the x is your time. Right now it goes up to 10. So, I don't know, maybe we take it up to 20 or something instead and just see. Sometimes you have to play around with it a little bit. You look at the graph, oh, I can't see anything. Maybe I need to change some things around. Thank you. And so, we'll start with this. Hopefully we'll see something. But if not, we can go back and change it. All right, so if that's hit graph. And there's the exponential decay. And here comes 50. Okay? So, we want to know where exactly do those two things cross each other. Okay? If you do trace, that'll give you an idea of where they cross. Yeah. Have you guys done that before? Oh, good. So second calc, intersect. We've done this sort of thing before. So we want to trace this thing to about where they cross, and then you hit enter 3 times, and it should pop it up for you at the bottom there then. So it's looking like about 4.8. Yeah, about 4.8. So that means that our solution then for this, t is going to be about 4.8, careful, years, right? So after 4.8 years, the bike has decreased in value to about $50. We just figured out there. Okay. So, any questions about that? Using the graphing part of the calculator to do that sort of thing? You guys are familiar with that then? Mrs. Court did work with you guys on that? Okay. Well, that's good to know. Okay. Then the only other thing I want to talk about is a particular function that gets used in money. And this is an equation that I wish everybody knew because they wouldn't be so stupid with their money if they did. It's called the compound interest equation. It looks super complicated, but it's really not so bad. It's that. It's called compound interest. Okay, so I got to help you out with what are all the letters in here. Okay, so is the amount of money that you're going to have when you're done. I should probably explain this a little bit more about what exactly it is and what does it do. Compound interest is a formula of if you were to put money, say, in like a bank account, and it earns so much interest. Have you guys heard about that? We're all familiar with that. So this bank account earns 2% annual interest or whatever, that sort of thing. Okay, this is the equation they use to calculate how much money you're going to have when you're done investing your money. So A is the amount of money you're going to have when you're done. P is called the principal. Which is the starting amount of money. Okay, so just starting money. So let's say I have $200 to invest somehow, so I'm going to put this $200 into this account. That's my principal. The R is the interest rate. Okay, and that's given as a percent. So it might say something like, it earns 3% interest or 6% interest or something like that. Is kind of the sticky wicket here for a lot of people. This is the number of compounding periods. And really the number of compounding periods, per year. All that is it's telling you how often it recalculates. So you got money, and let's say you're using an account that earns 2% interest every month. So it compounds monthly. So that means you're going to take your wad of cash, stick it in this account, and then after 1 month, they're going to add 2% onto it for you. And then they're going to take that new amount, and after another month, they're going to tack on 2% onto that. And they're going to take that amount, and after another month, they're going to tack 2% onto that. So that n is just how often in a year are they going to do that process of adding the interest in again and again and again. So it could be monthly, could be daily, could be semi-annually, which is twice a year. All different kinds of stuff, okay? And then the t is number of years. So how long are you going to keep the money in there? Okay, so you got those 5 things that you need. How much are you going to have when you're done? How much did you put in at the beginning? What's the interest rate? How many times is it going to calculate it in a year? And how long are you going to keep it in there? Okay, if you know 4 of those things, you can work to figure out the 5th or whatever it is. Okay, so I'm going to flip the page here. We're going to try this one time, and then we'll be good. So and these are usually going to be set up like story problems too, but it's just a matter of knowing where do the numbers go in the formula. So let's say you invest, let's say you got $500 into an account that earns, typical accounts right now are pretty low. In fact, I think most savings accounts are like 1% or something. Let's say you found a really good one. Let's say it's 2%. Okay. 6%, hold on to that one. Anyway, so it earns 2%. Let's do every month. How much will you have after a decade? So you've got $500 in an account that you don't touch for 10 years that earns 2% monthly. How much are you going to end up with? Okay, so I'll just write out the equation real quick here again. And by the way, I will not make you memorize this. I will give you this equation later. You just need to know what goes where. Okay? So, let's see if we can identify what's what. So, the A. Do I know what A is?
No.
That's what I'm searching for, right? That's how much I end up with. So I'm going to do this. A is question mark. That's what I'm searching for. What's the principal? What's the rate? 2%. Now, to put it in an equation, I have to turn it into a decimal, though. So 0.02. What's my N? 12. How many times in a year does it recalculate? It's every month, right? There's 12 months in a year, so N is 12. And what's my T? 10, because I'm going to hold it in there for 10 years. Okay? So now it's just a matter of taking all those numbers, dumping them in. What do we have? So P is 500.
Please excuse the interruption. We have a few announcements. Baseball players, the online Nike store closes Tuesday night at midnight. Also, baseball players, drink cup sales are due to Coach Odell by Tuesday at the end of school. JP's football players, if you missed the football banquet, please stop by Mr. Miller's room to pick up your certificates and numbers. Thank you.
Okay, so to keep things simple, just because I know where students normally make mistakes with this, I would take whatever's in the parentheses, do that first on your calculator. So you get 0.02 divided by 12, and you're going to add that to 1. It's really important, too, with whatever's in the base here, whatever's in the parentheses, you hold on to a decent amount of decimal points. So I'm going to go 0.00166, and then if I round it, 7. Okay, so I'm holding on to 6 decimal places there. And then 12 times 10 is 120, so that's 120. And then this is a lot easier to just type right into your calculator and then see what you get. So 500 times 1.001667 raised to the 120 will look something kind of like that. And so you end up with $610.62. Okay, so does that sound like a good deal to you? I'd say yes and no. It depends. You made $110 for doing essentially nothing. That's a pretty decent deal in my eyes. But it's 10 years, right? You got to do nothing with that money for 10 years. You have to avoid spending your $500 for 10 years, and then you can make 110 bucks. So, yeah, maybe not so great. So, savings accounts kind of work this way. So, if your parents probably, or you guys probably do too, have a savings account where you put money in and have a little bit stashed in there. And this is what's happening with it. They're adding interest every so often. You probably get bank statements, maybe over email or something, and they tell you how much interest you've earned and that sort of thing. And it's usually like pennies. Like they give you like a monthly statement, and you've earned, 12 cents in interest. Awesome. But over the course of a decade, that adds up a little bit. But yeah, so you just have to not do anything with it. Now, later on, we'll talk about these other things called annuities, where you actually keep putting a little bit of money in, and those have much better interest rates, and you can earn a ton of money that way. So I'll show you how much I'm making on my annuity and that sort of thing, but that's for another day. Anyway, okay, so I think we're good. I'm going to let you guys get started on your homework. I will stop my recording stuff here now, too. So.